Hey class, welcome back. We are tackling chapter 10. This is this in the light Bohr model chapter. This is my favorite chapter. Where this is called chemical bonding. Now we already talked about ionic bonding. We understand that the ionic bonding are between a metal and a nonmetal, right? So sodium chloride, sodium is the metal, chloride is the nonmetal, and it results from complete electron transfer, right? So an ionic bond is the electrostatic interaction we'll say electrostatic attraction between positive and negative charges, okay? That's from an ionic bond. But in chapter 10, we're going to cover covalent bonds, all right? So when two nonmetals form a compound, both nonmetals need electrons to complete their valence shell. This is the octet rule that we've already discussed previously. So because they're nonmetals, right, neither one really want to give up electrons. So since neither one want to give up electrons because they're so close to completing their valence, most nonmetals are 1, 2, sometimes 3 electrons away from completing their valence, they don't want to give up their electrons, so no ions are formed. Instead, when they come together, they decide to share electrons in order to complete their valence shell or their octet. So this sharing of electrons is called covalent or molecular compounds. We're going to call them covalent for the rest of this chapter. And covalent compounds, a covalent bond, is the sharing of, now one bond is 2 electrons. So the sharing of 2 electrons. So one bond equals 2 shared electrons. So we're going to cover bonding theories, which are really important. Bonding theories predict how atoms bond together to form compounds. It's important for us not only to understand how things are bonded, but it's also important for us to predict how things are going to bond, all right? They predict what combinations of atoms form and what combinations do not form. And this all comes back to whether or not two atoms can come together in such a way that they can share electrons in order to complete their valence. If there's no way for them to share them in a 2 electron per 1 bond situation, it's not going to work out. Bonding theories predict why salt, NaCl, and not NaCl2, and why water is H2O and not H3O, and we'll talk about that later. Bonding theories explain the shapes of molecules as well, which we will examine thoroughly. And the really important thing is all of this actually leads up to, especially for molecular or covalent compounds, leads up to predicting the shapes of molecules. Shapes of molecules are really important because it's the shape of a molecule that determines its physical and chemical properties. Okay, so if we can predict and we know how things will interact due to their shape, we can also use them in chemical reactions appropriately. So the first theory that we're going to talk about is Lewis theory. Lewis theory is named after G.N. Lewis. He's an American chemist. He died in 1946. We represent electrons in the Lewis theory. We represent electrons as dots and draw what are called dot structures or Lewis structures to represent molecules. So when we talk about Lewis structures, we're talking about Lewis dot structures. And it's true, these structures have tremendous predictive power, okay? Lewis theory can determine whether a particular set of atoms will form a stable molecule and what that molecule might look like. And although modern chemists also use more advanced bonding theories to better predict molecular properties, Lewis theory remains the simplest and very effective and very fast way of making everyday predictions about molecules. So, in Lewis theory, the valence electrons of a main group element are represented as dots surrounding the symbol of the element. Right? This is the real basic. This is just like the first page, right, of Lewis theory. This is called a Lewis structure or a dot structure. All right. Remember that the number of valence electrons for any main group element, except helium, which has 2 valence electrons, is equal to the group number of that element. Okay, so these are all the dot structures for all of the main group elements. And you'll just notice very simply, first column, there's only 1 dot to represent 1 valence electron. Second column, 2 dots to represent 2 valence electrons. Then we jump over to group 13, all right? 3 valence electrons, 4 valence electrons, 5, 6, 7, and then 8. And obviously 8 represents a full valence shell. And if we have a good understanding of this, we can sit back and look at how our electrons or how our atoms are going to bond so that they share electrons and therefore complete their valence shell. So we can arrange atoms in such a way, right, that gives us the Lewis structure of the compound, and it helps us understand the 3D structure and therefore its reactivity. But remember, the whole point of these valence electrons is that atoms come together to complete their valence shell. That's the driving force for atoms bonding, right? That's what makes 2 molecules or 2 atoms, 2 elements come together to form a bond. That driving force is that they want to complete their valence. So first, just talking about simple dot structures, we're going to start off with F2. All right, diatomic F2. We know that diatomic F2 is made up of 2 fluorine atoms, okay, not fluoride. Because remember, fluoride atom, it has an extra electron in it to make it IDE, negative charge. We're looking at 2 fluorine atoms. And what you're going to do is you're going to draw the dot structure of 2 fluorine atoms, which I have right here. If we go back and look up here, fluorine, right, it has 7 valence. So each fluorine atom is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons around it. Same goes with this one. 1, 2, 3, 4, 5, 6, 7. Now I've highlighted these guys so you can see that these are the lone electrons. So when we put fluorine together, as I did right here, this electron comes over, right? Or however you want to, they're rearranged. But you can see here that 2 electrons are in the center. Each fluorine shares its one red-blue electron. Each fluorine does. And once we put them together, you'll notice that each fluorine atom now has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, of course, we don't show the 2 electrons like this, the 2 shared electrons like this. We don't show them like that. We show them as a line over here. All right, we represent the 2 shared electrons as a line, and this line is a covalent bond. Now you'll also notice here that I have these dots, these non-shared electrons, still represented as dots. That's important. We keep that. These are called lone pairs. Okay, they're also called non-bonding electrons or non-bonding pairs. Either way, these guys play a really important relationship when we start predicting the shape of molecules. So when we draw Lewis structures for compounds, we have to always include the non-bonding electrons as well. But the bonding electrons we represent as a line. Okay, we'll do another one. We are going to do, actually, let me do. I'm going to do this real fast. So now we're going to do, just really quickly, we're going to do CH4, which is methane. All right. And if we want to predict the 3D structure of CH4, the first thing that we're going to have to do is we're going to have to write a dot structure or Lewis structure for methane. Now, at first, what you guys are going to have to do is you have to understand, we're going to just do, there's one carbon atom, right? Each carbon atom, or the one carbon atom, has 4 valence electrons. Just go ahead, you can see here, carbon, 4 valence electrons. And there are 4 hydrogen atoms. Each hydrogen atom has 1 valence electron associated with it. So I'm going to put 4H, okay? Now what we're going to do is we're going to arrange these guys in such a way that each hydrogen is going to share its blue electron with a carbon atom, and the carbon atom is going to share each one of its black electrons with each hydrogen. Sorry, hold on a second. So I'm going to draw this. Actually, plus, I'll draw it like that. Okay, so I'm going to have carbon, 1, 2, 3, 4, and then change it to hydrogen, and then each hydrogen is going to bring 1 electron. There's 4 of them. Okay, so this is technically a dot structure, right? And what you'll see here is that carbon, now that it has, how many electrons is surrounded by carbon? 1, 2, 3, 4, 5, 6, 7, 8. So carbon has a full octet. And then hydrogen is one of those exceptions. It doesn't need 8 electrons. It only needs 2 because it only has, remember, a 1s orbital. So it already has 1 electron. So it's only going to need 1 more to have a full valence. And each hydrogen atom has 1, 2. So this guy's good, 1, 2, this guy's good, 1, 2, this guy's good, 1, 2, and this guy's good. Now, of course, we don't show the dot structure like this because we don't represent bonds with dots. We represent bonds as lines. So we're going to say so even though there are no lone pairs, there's no dots here, this is the Lewis structure for carbon. Sorry, this is the Lewis structure for methane. And you'll see that I have it written right here, okay? So again, 4 hydrogen atoms, each bring 1 electron to the table, 1 carbon atom, which brings 4 electrons to the table, and we arrange the electrons in such a way that everybody has a full octet, and then we replace the bonding electrons with lines, and then we have a complete full valence structure. All right? So you'll notice a pattern here, and the pattern is that we add up valence electrons. So I'm going to do another one really quickly. I'm going to do O2. You saw it on the slide just a second ago, but I'm going to do it again. So we're going to do the Lewis structure for O2. All right. So first of all, oxygen, we got a valence electrons. Just go back up here. Oxygen has 1, 2, 3, 4, 5, 6. Each oxygen, and there's 2 of them. Oops. Sorry about that. So 1, 2, 3, 4, 5, 6. Plus 1, 2, 3, 4, 5, 6. All right. So then what we're going to do, we already know that O2 is going to bond, right? So I'm going to put 1 here and 1 here. And then I'm going to take these 2 electrons, right? I'm going to put them right here. Okay. Then I'm going to start placing everything else. I'm going to place the, let's see if I can do this is faster. So these 2, we're going to go 1, 2, actually I did it on the left one. 1, 2, 3, 4, 5. And you'll see that the 6th electron I put here. Now for the other oxygen, 1, 2, 3, 4, 5. Okay, so I have a bond in between these 2 oxygen atoms. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have a total of 12 electrons around here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But when I count up the electrons for each oxygen, do I have an octet? 1, 2, 3, 4, 5, 6, 7. Same goes for this guy right here. 1, 2, 3, 4, 5, 6, 7. So each oxygen still needs 2 electrons. Sorry, each oxygen still needs 1 more electron to complete its octet. So what I'm going to do is I'm going to force, and I say force, you know, that's not nice, but this electron right here is alone and this electron right here is alone. So what I'm going to do is I'm going to take this one and I'm going to bring it in the center. All right, that is dark. I wonder why that came out differently. Either way, so I'm going to erase these guys. Now, let's take a look and see how many electrons each oxygen has. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So each oxygen has an octet, which is what we want. So now I got to replace my lines, or my shared electrons, with lines. So oxygen, and there are 2 sets. That means that each oxygen has a double bond, and then I have to bring over the non-bonding electrons as well. I'm going to make this a little bit bigger. Okay, so there you have it. This is the Lewis structure for O2, where these dots, again, are the non-bonding. All right, we always show, most of the time, we're going to show these as pairs, if we can. Okay, sometimes they don't pair up, and that's a whole other thing. It's called a radical. You've heard of free radicals? Free radicals are something where there's 1 electron by itself, and it's not paired up in a non-bonding pair. There's only 1. But again, that's more OChem than anything else. So this is where we have O2 is an example where we have 4 total electrons shared between 2 oxygen atoms. This is a double bond. Okay, this is a double bond. So a double bond is 4 electrons, and then we can also have a triple bond, which is 6 electrons. And we doing nitrogen? Oh yeah, I'll just go ahead and let's do nitrogen right here. Okay, so N2 is each nitrogen, go up to look at its valence, 1, 2, 3, 4, 5. Each nitrogen has 5 valence electrons. Okay, so they're going to have to come together again to form a bond. Now, if we just take a look and see, 1, 2, 3, 4, 5. So this nitrogen needs 3 more electrons, right, to have a full valence. Same goes with this one. So we're going to have 1, 2, 3, 4, 5. How are we going to get 3 more electrons over here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. So the first thing we can do is we can take these 2 guys, right? I'm going to draw. And make them bond. Okay, that's good. So that now each nitrogen is going to have 1, 2, 3, 4. 1, 2, 3, 4. All right. But this nitrogen only has 6. This nitrogen only has, and this nitrogen only has 6. So we need 2 more. 1, 2, 3, 4, 5, 6, right? We're going to need, this guy needs 2 more. So what are we going to do? Well, we can sit back and say, all right, we'll take now these 2 electrons and move them over. Okay, did that. Now let's take a look. Remember, because we can't add electrons, we just have to arrange them. 1, 2, 3, 4, 5, 6, 7, 8 for this guy right here. So this nitrogen's good, but guess what? This one still is not good. 1, 2, 3, 4, 5, 6. This one still has 6. So that means we're going to have to take these two and place them here. All right, now let's take a look. 1, 2, 3, 4, 5, 6, 7, 8 for this one. 1, 2, 3, 4, 5, 6, 7, 8 for this one. So now each nitrogen has an octet. So of course, when we actually complete our Lewis structure for N2, we are going to draw our lines, or our shared electrons as lines, and then we keep the lone pairs. There. So this is the Lewis structure for nitrogen, and this guy's a triple bond, and a triple bond is 6 electrons. Okay, the sharing of 6 electrons is a triple bond. Okay, so again, here we go. Here's nitrogen right here. There's the triple bond. And I don't know if you've ever heard that liquid, or that nitrogen is a very, very stable compound. It is. It's very, very hard to, this is actually really interesting. It's very hard to break this triple bond. Okay. It's very strong. So, and this is a very, so there's a lot of energy and research and, a lot of energy that is put into collecting into and breaking this triple bond. All right, and this is actually this is called the Haber-Bosch process, where we actually break this triple bond to make ammonia, and that ammonia is a precursor to fertilizer. Okay, so a lot of actually fossil fuels and greenhouse gases are made and released into the atmosphere just because we want to break this triple bond in order to make NH3 so we can make fertilizer so we can grow food. All right. And if you really want to talk about that in detail with me, please email me. It's a big problem. Okay. So again, more on covalent bonds. A single bond represents 2 electrons, and a double bond is 4. And a triple bond is 6. Okay. Again, in all these situations right here, we have the lone pairs are always shown. All right. The non-bonding pairs are always shown, and the bonding electrons are represented as lines. So, in order to draw more Lewis structures, okay, what we're going to do is, and I should have done this before, so I'll just go ahead and bear with me. Sorry. Redacted version, right? In order to draw more complicated Lewis structures, and really this is the method that you're going to use to draw all Lewis structures for the rest of this semester. This is the method right here that you're going to use. So first, let's start off with SO2. All right. So we have SO2. What are you going to do? Are you going to do all this stuff that I was doing before, where you draw little dots and do this and do that? No, you're not going to do that. What you're going to do is you're going to follow this very straightforward method. Your book teaches it a little bit differently, but I really like this, so I encourage you to do it this way. More difficult Lewis SO2. So the first thing that you're going to do is you're going to count up the valence electrons. So you're going to say, all right, well, I know that sulfur is right under oxygen on the periodic table. If you don't believe me, hopefully you have a periodic table right in front of you. Sulfur brings 6 valence electrons. Oxygen also brings 6. And there are 2 of them, right? Because we have a 2 right here. So that's 2. So we have to multiply that by 2. So that's a total of 12. And we add them together. That is 18 valence electrons that we have to work with. 6 from sulfur, 12 from the 2 oxygen. Okay, now I'm going to delete that, right, just so I have room. Then what you're going to do is count the number of electrons needed for the octet rule, right? How many electrons in a perfect world, right? Not in this, we only have 18 to work with, but we need to find out how many of those are shared. So the first thing that we're going to have to do is we're going to have to figure out how many electrons total is needed so that each atom has a full valence. So that means every atom, sulfur is going to need 8, oxygen is going to need 8, and then times 2, that's 16, right? So 16, and then we add these together. 16 plus 8 is 24 electrons. So we have 24 electrons needed for everybody to be happy, all right? Then what you're going to do is you're going to subtract the needed from the available. And that's going to give you E shared, electrons shared. So you're going to take E needed, which is, for us, it's 24. And you're going to subtract E shared, which in this case was 18. That's how many we have to work with. And that gives us 6 electrons. Okay? So this 6 electrons here, this says that in this structure, 6 electrons out of the 18 that we have, 6 of them are going to have to be shared in order for everybody to have a full octet. So then what you're going to do is you're going to take this information here and you're going to figure out the number of bonds that this represents. So you're just basically going to take, so this is, so again, this is E shared. Not sure. Right? So a number of bonds is going to be E shared minus, or sorry, divided by 2. Why 2? Well, because each bond is worth 2 electrons. So 6 divided by 2 is 3. So that means we have, sorry about that, 3 bonds. Okay? We took the E shared, which we got from taking E needed minus E, I'm sorry, this is not E shared, yikes. E have, my bad. All right, so we have E have, or E needed minus E have equals E shared. And then E shared divided by 2 gives us the number of bonds. So there's 3 bonds. So then what you're going to do, you're going to arrange, then the next step is arrange the atoms and insert the bonds. So how are we going to arrange SO2? Does it look like, which one? All right. Well, for this class, all right, and essentially, basically up until you get into organic, most of the time, if you have a single atom and then 2 atoms, that single atom is going to be the one in the center. All right, so you're going to locate the central atom. That's the first thing that you're going to do. So I should say identify. Okay. In this case, most of the time it's the solo atom. It's also the atom that has the most, we'll say, metallic character. All right, that's what we've learned so far. So if you remember your metallic character rule, metallic character increases as we go from right to left of the periodic table, and it also increases as we go down. Okay, so since sulfur is below oxygen on the periodic table, it's going to have more metallic character. And just a spoiler alert, we're going to relate metallic character to electronegativity in just a little bit. So you're going to place your atoms. Sulfur is going to go in the center. Then, just because we only have 2 more, we're going to place 2 oxygen atoms around the sulfur. All right, now we have to place bonds. We have 3 bonds. So 1, 2. Okay, where does the third one go? Well, it's either here or here. It doesn't necessarily, in this case, it doesn't matter where you put it. All right, so now we put our bonds. Arrange the atoms and insert the bonds. All right, we just got rid of 3 bonds. That means we got rid of 6. We got rid of the shared. We got rid of 6 valence electrons. We had 18 to start off with, so now we have 12 remaining. Okay, so now we're going to have to place the 12 remaining electrons around each atom to make sure that the octet rule is followed. Okay, so 12. So the first thing that I like to do is I like to place electrons around the outside atoms to make sure that they have a full valence. So this oxygen right here, it already has 1, 2, 3, 4. So now 5, 6, 7, 8. Okay, so now that gives me, since I just used 4, right, that's going to give me now 8 remaining. Now I'm going to go over to this guy over here. It, as of right now, only has 2 electrons associated with it. So I need to give it 6 more. So since I just got rid of 6 electrons and I had 8 remaining, now I have 2. And the only other place, this has a full valence, this has a full valence, so the 2 remaining electrons are going to go on sulfur. And now we have, now we have 0 remaining electrons. Then what we do, after we finish everything, we're going to go back and count and make sure that everybody has a full octet. Again, this oxygen right here, 1, 2, 3, 4, 5, 6, 7, 8, good. 1, 2, 3, 4, 5, 6, 7, 8, good. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's good. You also want to go back and double check and make sure that you haven't added or removed electrons, right? We only have 18 to work with. So you should only have 18 electrons here. Ever. You should only ever have 18 electrons. You have to, you can only use the amount of electrons that you have available to you. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's 18, all right? And turns out, there we go. So this is the Lewis structure for SO2. So let's do the same thing for all of these, okay? So what I'm going to do is I'm going to copy. And it's really important, you'll see this here, this rule, this example that I have right here, this example I should say, this only works when if the octet rule is followed. There are some instances where the octet rule is not followed. There are some atoms that can have more than 8 valence electrons. You will cover those in detail in Chem 200, okay? You'll cover those in detail in Chem 200, but for this class, because this is an intro class, we're only going to be working with compounds that follow the octet rule. Okay, so I'm going to take this. Okay, so you have that. And the first thing we're going to do water. H2O, okay? So the first thing that we do always is we add up our valence. So H2O, all right? Oxygen, 6 valence electrons. Hydrogen has 1 valence electron, and there are 2 of them. So that's a total of 2. And then we have a total of 8 valence electrons. So that is E-half. Okay. Then we're right here. Now we're going to count the number of electrons needed for the octet rule. So this is, remember, we called this E shared. So E shared is equal to, oxygen is going to need 8 valence, right? Hydrogen needs 2. Remember, because of the 1s orbital, it needs 2, not 8. So, and we have 2 hydrogens in this compound. So that's a total of 4. Add these 2 together. That's going to give us 12, right? So E shared is equal to 12. I don't know if you guys have noticed, but I got my new stylus finally. So this stylus is way better than the ones I've been using. It's actually the oldest too. I tried to get really nice ones, but they just didn't work out. And so I went with the bamboo stylus, in case you were curious. Okay, so now we need to find out how many E shared there are. So remember, E shared, sorry, this is not E shared. What's wrong with me? This is E needed. Okay, so remember, E shared is equal to E needed minus E have. Okay, so that means E shared is going to be equal to 12 minus 8 equals 4. And that is, again, E shared. Okay, now the number of bonds equals E shared divided by 2. So that's going to be 4 divided by 2, and that's going to be 2. That's the number of bonds. All right. Now we're going to arrange the atoms and insert the bonds. Again, oxygen, solo, right? Here's the deal. Hydrogen has a little more metallic character than oxygen, but oxygen is going to be in the center. Okay, it's the solo atom. So most of the time too, like I said, I think probably the easiest thing to do is always just to remember that the solo atom is going to be the atom that goes first, okay? Or in the center, I should say. So now I'm going to place oxygen, and then I have my 2 hydrogens, okay? I have 2 bonds here that I calculated, so I'm going to place my 2 bonds. So that got rid of 4 electrons. And how many do I have to start off with? I have 8. All right, so remaining I have 4 electrons left over. Okay, so I'll put remaining. Now what I'm going to do is I'm going to make sure that each atom has the appropriate number of valence electrons. Each hydrogen only needs 2, and there's a bond right there, so this hydrogen now has 2, this hydrogen now has 2, so the 4 remaining valence electrons are going to go on oxygen. Just like that, okay? Then I'm going to make sure that everybody's happy. I already told you that hydrogen was happy. Now we're going to look here and look at oxygen, count up its valence. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's good. So this is the valence structure for water. Okay? I'm going to delete this whole thing. And we're going to do it all over again. Now we're going to go and we're going to do the next one. We're going to skip, actually we're going to skip this one. We're going to do this one right here. NH3, ammonia, NH3, okay? So, and I'm going to move this over here. The first thing that we're going to do is we're going to add up our valence electrons. Nitrogen brings 5 valence electrons. Hydrogen, each hydrogen brings 2. And there are 3 of them. So that's a total of 6. So we're going to have 11 valence. So 11 is going to be E have. Equals 11. Now what we're going to figure out is we're going to figure out what our E needed, or E need if you want. All right, E need is going to be, for nitrogen, we need 8, and for hydrogen, we need 2, and there are 3 of them. Oh, whoops. I'm sorry, you guys. Let me go take this back a step. I just realized I made this mistake, so aren't you glad that I caught it before I started to go on? Each hydrogen brings 1 valence electron. There are 3 of them. So we're going to, our E have, is actually 8. Okay. So now I'm going to bring it back to over here. So our E need, nitrogen, 1 valence electron, or 8 valence electrons is what it needs because it's for a full octet. And each hydrogen only needs 2, and there are 3 of them. So that means a total of 6. So our total E need is 14. All right. Then what we're going to do is find out what E shared is. E shared is going to be E need minus E have. So E shared is, E need is 14. E have is 8. So that is going to be 6 shared. All right, E shared is 6. Now we're going to say, because we have E shared, I'm going to bring it over here, number of bonds equals E shared divided by 2. So that is 6 divided by 2, which is 3. So there are 3 bonds. Okay? Now we're going to take this, we're going to arrange the atoms and insert the bonds. NH3, right? Just to let you know. Sorry, I deleted that. NH3. Nitrogen is the central atom, and we're going to flank it with 3 hydrogens. And because we're working with 3 bonds, I'm just going to go ahead and place the 3 bonds here, here, and here. Okay, so that means that we started off with 8, right, valence electrons, or electrons. We used placed the 3 bonds, so that got rid of 6 electrons, gives us 2 remaining, and the only place that we can put the 2 is right here. All right, hydrogen, each hydrogen has a full valence. And let's make sure that nitrogen has a full valence now. 1, 2, 3, 4, 5, 6, 7, 8. All right, and just to double check and make sure that your E have, you don't have any more than you in here than what you actually have. 2, 4, 6, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. So that's our E half. Okay, so this is the valence for ammonia. And we're going to do one more. Okay. The next one we're going to do is we're going to do CO2, and I will do these two when we talk in Zoom. So CO2. I'm going to do this one a little bit, just a little bit differently in the sense of I'm going to color code it. Okay, so first of all, add up the number of valence electrons. So carbon has 4 valence. Oxygen has 6, and there are 2 of them. So we're going to put 12. All right, so E have is 16. All right. Now what we're going to do is we're going to calculate E need. All right. Carbon needs 8. Oxygen needs 8, and there are 2 of them, right? So that's 16, and then 16 plus 8 is 24. So E need is 24. Okay. Then we're going to calculate E shared. That is going to be equal to E need, which is 24, minus E have, which is 16. And that's going to give us 12. Okay. And then finally, number of bonds. Is going to equal E shared divided by 2, which is 6. Did I do that right? Yeah. Let me make sure I did that right. Yeah, 24. Let me make sure. This is at the end of the day. I don't know if you guys have noticed. What's wrong with me? What did I do this wrong? This is wrong. This is so wrong. Sorry. Life is hard sometimes. So 8 divided by 2 is not 6. Simple math, guys. Simple math. Okay. So we have number of bonds is equal to 4. Okay. So we have 4 bonds. So what we're going to have to go back and do is we are going to place our central atom, carbon, flank it with 2 oxygens, and we're going to put down 4 bonds. And I'll do it in purple just to... There you go, right there. All right, so because we placed these 4 bonds, that means, and we started off with 16, that was our E have, right? 16 is our E have. I don't know why I said 12 here. I really honestly have no idea. E have is 16, okay? And then what we're going to do is we're going to subtract the 4 bonds, right? That's 8 electrons. So that gives us a remaining amount of 8 remaining. Okay, so what are we going to do? Where are we going to put this 8 remaining electrons? Well, we got to sit back and see who has, if everybody have 8 valence? Let's take a look. Carbon does already. I can see 2, 4, 2, 4, 6, 8. So carbon has 8 valence electrons. So it can't take any more, right? It can't take any more because remember its valence. This is the 1s. Here's the 2s. Here's the 2p. Right? Its 1s isn't even involved in bonding. The 1s orbital, the electrons in the 1s, those are the core. It's not involved in bonding, but it has, how many electrons did I say carbon has for valence? 1, 2, 3, 4. So, and it now has it now has 8 valence electrons right here. So it cannot take any more electrons. So it's stuck. No lone pairs are going to go on that. So the 8 remaining electrons are going to go to each oxygen. Okay? Because each oxygen has 2, 4, only has 4 electrons associated with it at this point. So I'm going to go in and put 1, 2, 3, 4, 1, 2, 3, 4. So I just placed 8 electrons in there. So now we have 0 remaining valence. All right. And this is the Lewis structure for CO2. All right. Where now, does it matter necessarily where you put these lone pairs? If you put them here or you put them over here? No, not at this point. It does not matter. What we're going to do in the future is we're going to take the Lewis structure and then we're going to convert it to a 3D structure. So we need to get really good at writing Lewis structures for simple compounds, and then we can take the correct Lewis structure and move on and convert it to a 3D structure right here. So like I said before, you guys can try this one on your own, these two on your own, and then what I would do is I'll actually do these in our Zoom lecture, okay? Okay, so one last thing really fast. Lewis structures for polyatomic ions are a little bit different, all right? The only reason why they're a little bit different is if I zoom in here, you will see that this is a polyatomic ion, and remember, nitrate has a negative charge associated with it. That negative charge actually means something when we're talking about Lewis structures. That negative charge means that there's since it's just a -1, that means that there's 1 extra electron floating around in O3. Okay? So you have to keep that in mind when you're adding up your valence. So I'm going to do NO3 up here again. Sorry, real quick. Okay, remember NO3, polyatomic ions, Lewis structures. So again, NO3, and you have to take into account the charge. Okay, so to add up the valence electrons, nitrogen has 5, oxygen has 6, and there are 3 of them. So, sorry. Palm recognition, not the best. Or non-existent. So that's 18. All right. So normally this would be finished, but we have this negative charge associated with it. So that means we have to, and I'll just put circle that negative charge. That means we have to add 1 electron. So now we're going to add everything up. All right, 18. Now I'll do this. 18 plus 5 is 23 plus 1 is 24. I'm laughing, by the way. Can't see it. All right, so this is my E half. Okay, E half is 24 electrons. Okay, my E shared, or E need, is going to be calculated the same way. All right, nitrogen needs 8, oxygen needs 8, and there are 3 of them. All right, so 32. That's my E need. So my E shared, right, is going to be E have, which is, I'm sorry, I'll start off E need, which is 32, okay, minus my E have, which is 24. All right, and that is going to equal 8. Okay. So now that we have our, and this is our E shared. All right, I do this out of habit. That's just a negative sign, right? Don't get confused about that. Whenever I write E, I always do a negative like that. It's just to indicate, right, electrons, that it has a negative charge associated with it. All right, so now that we have E shared, we're going to figure out our number of bonds. So number of bonds is equal to, sorry, I hope this, I want this color coding to be helpful to you. I hope that me switching back and forth isn't distracting. 8 divided by 2, so that's going to be equal to 4. So there are 4 bonds associated with this, okay? Our central atom is nitrogen, and then we're going to place the oxygens around it. Okay, actually I'm going to do it like this. Okay, that's because I know what this looks like, so I know what to do. So then I'm going to place, obviously, our obvious bonds, which is 1, 2, and 3, but we have 4 bonds. So where am I going to put the 4th? Because there's an oxygen here, and an oxygen here, and an oxygen here, and because if I were to just, I don't know if I can do it. No, it won't let me do it. I was going to try to rotate it. Because this oxygen isn't any different from this oxygen, which isn't any different from this oxygen. Where I put the last bond doesn't matter. All right. One student might put it here, the other student might put it here, or the other student might put it here. That does not matter because all of these oxygens are originally equivalent. Because I can put that double bond anywhere, this is called, resonance. All right, so this is called resonance. And a resonance structure, a resonance structure for NO3 would be where the double bond is on that oxygen or on this oxygen. Okay, so either way, the way that we should say it, these are the resonance structures. We're not finished, but in terms of double bond, these are the resonance structures of NO3, of the nitrate anion. These guys are all equivalent, right? And that the real structure in real life is a mixture of all of these, okay? Because the double bond, it's equal, right? It doesn't matter. Double bond could be here, it could be here, it could be here, okay? We'll talk about resonance a little bit more, but I just wanted to introduce it to you quickly. Okay, so we're going to focus on this one for right now. I'll put resonance on the bottom. All right, so you just remember resonance. So we just got rid of 4 bonds. That's 8 electrons, okay, that we got rid of. We started off with 24, right? So we have 16 electrons remaining. So where are we going to put them? Well, nitrogen, you'll notice, has plenty of electrons. It has 8. It doesn't need any more. 2, 4, 6, 8. So nitrogen's fine. Let's look at the oxygen with the double bond, because obviously the oxygen with the double bond, it has more electrons than the oxygens with a single bond. This oxygen right here, this is driving me nuts. This oxygen right here has 2, 4 electrons associated with it. It needs 8, so I'll just go ahead and give it 4 more. 1, 2, 3, 4. Okay? Since I did that, I'll just go ahead and do that with every single one. Okay, that has a double bond. So I just got rid of, if we're going back to this guy right here, I just got rid of 1, 2, 3, 4. So I'm going to, now we have 12 remaining, 12 electrons remaining. These 2 oxygens are equivalent, right? Each one has 2 electrons associated with it. Each one only needs 6 more. And it turns out I can divide 12 by 6. And give each oxygen 6 electrons, okay? And once I did that, now I have no more electrons remaining, okay? So this, what I'm going to do here is I'm going to move all of these down. And I'm going to do the same thing for all the other ones. I kind of feel like this is a little bit too big, so. And then just to make it a little bit more pretty, go ahead and just get rid of these and okay. So just delete this for a second. If I were to ask you for a Lewis structure, a legit correct Lewis structure of NO3, you would do this. You would do one of these guys, right? It would be one of these guys, depending on the type of person that you are. Are you going to put the double bond here? Are you going to put it here? Are you going to put it here? Again, it doesn't matter, just that I have one relevant or one correct Lewis structure. So you would put, again, I'm just going to do this just to show you. Okay, and then you have to make sure that you have all of your lone pair. And if I were to ask just for one, then you would put brackets around it. This would be your final answer. And then you would put a negative sign. The brackets indicate that there's an extra, with the charge, the brackets indicate that there's a negative atom, or there's an extra electron floating around it here. How many? 1, because the overall charge is -1. And you have to put the brackets, okay? If I ask you to give me all of the relevant resonance structures for NO3, you would do all of these guys, and then you would put a bracket around the whole thing, and you would put double-sided arrows in between each, indicating that it's going back and forth, and then you would put a negative sign on the outside, okay? So that's how you would do it. Again, we'll do more practice with resonance, but resonance structures are Lewis structures where you can put, there's more than one place a double bond can go and have it be equivalent. Okay, SO2, I'll go back up here. SO2 is a really good example of resonance structures, right? I put the double bond here, but one of you could put the double bond here. All right, so these would be two equivalent resonance structures, and you wouldn't put a bracket around them because there's no charge associated with it. Okay, I'm going to do one more and then we're going to stop. I'm going to do NH3. That's the only polyatomic cation that you guys need to know. Sorry, NH4, ammonium, ammonium, okay? Sorry, I'm just going to delete these real quick. Okay, so ammonium is NH4 plus. Okay, so what do? Before, we knew that negative signs, polyatomic ions with negative charges, we add electrons. So polyatomic ions with positive charges, we subtract. So NH3, first add up our valence. Nitrogen has 5, right? Hydrogen has 1 times 4, so a total of 4. That would give us 9, but since I have a plus charge, I have to subtract 1. Okay, so that's going to give us 8 for EHAV. Okay. E need, N for nitrogen, 8, hydrogen, 2. There are 4 of them, so that's 8. So we have a total of 16. E need, E shared is equal to E need minus E have. Okay, so it looks like all of the electrons that we have to work with are all in bonds too, by the way. And then finally, the number of bonds is equal to E shared divided by 2, which is 4. Okay, we're going to place our central atom, nitrogen, and then we're going to place hydrogens around it. And then we're going to place our 4 bonds. Our 4 bonds are all of the electrons that we have to work with, right? We only have 8, so we just placed 8 electrons. We don't have any lone pairs in here, but we do have a positive charge, right? Because it's ammonium. So we're going to have to indicate that there's a positive charge, that there's 1 less electron in here by indicating brackets with the plus charge. Very important. Brackets plus charge. Otherwise, it's not. If there's a charge associated with the ion, then the polyatomic, then we're going to have to indicate it with brackets and charges. Okay, we're going to stop here, and then when we pick up later, we will talk about Lewis structures again of, we already did polyatomic ions, of oxyacids, okay? Oxyacids. All right. Talk soon.